Well, thank you everyone for joining Interface today. We're very excited to present to you a discussion conversation about calibration, a topic that is very near and dear to Interface's existence, but also to many of you. And again, thanks for joining. This is one of our Force Leaders events that we host throughout the year. We are recording this event so that we can then put that on our website and YouTube channel for you to view later. If you have any questions, we'll also provide everyone a link to the recording. Today, we brought together a decade's worth of experience with Elliot and Brian, who will be joining us with Chris. They all have a lot of great experience working with clients all over the world in finding calibration grade equipment, but also providing different services that we've been doing for, well, 54 plus years. So with that, I'm going to hand it over to Elliot and Brian to take us through today's agenda. If you have questions during the event, please use the chat feature. We'll be watching for that and try to answer as many as we can through the end. Again, thanks for joining. Elliot?
Actually, Jamie, I'll start things off. Thanks everybody for joining. Metrology, obviously, calibration, big topic. We're going to do the best we can to touch on some high-level aspects, do a little bit of deeper dive in some areas. Given the talent and experience of some of our attendees today, of course, I'm sure there's going to be some questions that Elliot and I may not be able to answer, but we'll do the best we can. And if we can't answer them today, we'll get back to you later. So on that note, these are some of the different aspects that we're going to cover today. Just metrology perspective overall, talk about calibration methodology, what's behind it, and of course the reasons why it matters, why it's important. Touch on uncertainty. That's another area that can be a deep dive, but we'll do an overview there on how to approach it, especially if you're a calibration lab yourself or you're doing calibrations in-house. And we'll talk a little bit about errors. What are some of the errors that factor into calibration or measurement uncertainty, if you will, in your testing. And then different aspects of doing system calibrations, different approaches there. We'll talk a little bit deeper on the calibration labs, best practices, and of course, fixturing and how to optimize your cals that are actually being performed. Past that, we'll do a little bit of product and interface capabilities, and we'll cover some of that. And then we'll wrap it up with some do and don't tips and FAQs. So on that note, Brian Peters, VP of Sales. We have Elliot, National Sales Director. And I believe Chris Brandenburg's also on. I don't see his camera, but he should be joining as well for some of the sections. So Elliot, I will hand this over to you now.
Sounds good. Thank you, Brian. So again, kind of a high-level overview here. So we'll kind of start at the beginning with what is metrology. It's defined as the science of measurement, embracing both experimental and theoretical determinations at any level of uncertainty in any field of science and technology. In metrology, standard is an object, system, or experiment that bears a defined relationship to a unit of measurement of a physical quantity. And it's coordinated by national laboratories known as National Metrology Institutes, such as NIST, Inmetro, or PTB are some examples of that. Next slide, please. In terms of the traceability hierarchy, it all goes back to the International System of Units, tearing down through national standards or national metrology institutes, such as NIST, down to calibration houses or factories, such as Interface, back to our standards or our masters or our reference standard load cells, and then down to our customers, or your customers for that matter, transfer standards or companies' product equipment, out to a final product that the customers are manufacturing or providing to the general public. Next slide, please. So again, global network standardizing measurement units, and calibration is the action taken at each step in the metrology network. It's incredibly important to make sure that processes are controlled and defined. Systems are built around these calibration requirements. It's important from a reliability perspective, making sure that these processes are controlling actions and steps in manufacturing. Obviously, accuracy is another component there, and quality control would be another point of that, and scientific method would be another point to touch on there in terms of criticality. Next slide, please. So kind of the basic what, why, and how behind calibration. So load cell calibration 101, kind of the what. Loosely can be defined as the set of operations that compares the accuracy of a measuring instrument of any type, such as a load cell or torque transducer in this case, against a recognized standard. Common misconception is that there's some sort of adjustment process that goes into a lot of these calibrations for load cell, when in fact it should be more commonly referred to as almost a characterization, where we're actually characterizing the performance of a load cell or torque transducer against that known standard. That said, this calibration process can include some sort of adjustment that is done mostly on the system level, to bring that measurement system back into the tolerance or back into alignment with the standards being compared against. Next slide, please. Why do we calibrate? All load cells are subject to some sort of performance degradation due to mistreatment, drift, or aging. You're going to see some change in sensitivity over time. Perhaps the load cell is being used in a very abusive environment. Perhaps it's within the first couple of years of manufacture, and you're going to see some drift happen as a function of epoxies and different materials in the load cell aging. So no matter what, you're going to see some change in output from the load cell. Traceability and quality system requirements, holding to those quality system or ISO standards. Pre and post test verification. Some folks need to make sure that number one, the load cells or torque transducer are verified and characterized prior to a test, and then of course post test verification that the pre-test still holds true. And even load cells manufactured to the highest standards require regular calibration. So even our metrology grade load cells do require calibration. We'll touch more on that later. Marcus, I see a couple questions that are pretty good there. We do perform some adjustments to the load cells during the manufacturing process, primarily our low profile load cells. And that's primarily based around moment compensation. So you could view that as a calibration in a way. However, it's slightly different than our final calibration process that defines the actual sensitivity of the load cell. It's more of like optimizing the load cell through the production process, I would say. And you are correct, we do trim some load cells. That is done as a step in the calibration process, and is more of if a customer desires to have a set or trimmed output. So we'd adjust it to a nominal sensitivity value.
And that's typically done electrically, of course.
Slide, please. How do we calibrate load cells, torque transducers? There's a couple different methods of force application for these calibrations. Number one is to use a direct dead weight. You can do this with hand weights or known masses or specifically built dead weight stands. These offer the lowest uncertainties down to 0.005%. There are some trade-offs. It can be slow. It does take time for the weight stack to stabilize once the load is applied. And as you might imagine, it can be somewhat space inefficient in that you have a large amount of mass. It does take a large amount of room. Another technique would be leveraged dead weight, where they take a dead weight stack and apply it to a lever arm. This offers uncertainties down to 0.01%. This does still share some of those same drawbacks that the dead weight has, in that it can be slow and it can be space inefficient. Again, we're dealing with mass. It does take room. Hydraulic force generation and load cell intercomparison, that is down to 0.04% uncertainty and is the fastest and most space efficient option at interface. That's primarily what we do with the hydraulic intercomparison. Slide, please. For torque calibration, torque is loosely defined as force at a given length. So we accomplish this in two different methods. Number one, we have dead weight and lever arms. We have an example here on the right-hand side of the slide. This is an air bearing type stand where we have a shaft suspended by two air bearings, and there is a lever arm assembly that is attached to said shaft. It's tough to see there, but there's two nylon cups on the other side, and that is where the torque transducer would be fixtured in. And then you can see we have a dead weight stack applied to the end of the lever arm, applying a calibration mass. And then the other method, past a certain point, we transition to hydraulic actuation. So the image on the left is our hydraulic stand. This is about a 100,000 pound-inch stand. So we have a hydraulic actuator and a torque transducer in line. And there's a gap there you can see where we would fit our DUT in line there. Next slide, please. Reference standards. So we use reference standard load cells and torque transducers. At Interface, we use a very high-grade version of this. It's our 1800 series. It's a monolithic design, meaning that the calibration adapter is integral to the load cell. These have primary standard calibrations performed across multiple different force ranges, and this allows us to use the sensor to meet a variety of different desired calibration points for our customers and for our production requirements. And then we use a proprietary software set and electronics that utilize the polynomial curve fit data. This helps us eliminate as much possible the nonlinearity error, and also allows us to generate some different calibration points as needed for customer and production requirements. And we address hysteresis error by using multiple descending force calibration ranges and extrapolating across the two. Our most valuable load cells, they are the ones with the most calibration history. So we have load cells out on our production floor that have literally decades of calibration history, so very reliable and extensive history on those. Slide, please.
All right, I'll take over from here. Next slide, Jamie. All right, so why does it matter? Well, first reason, as everyone can understand, is trying to understand your component level uncertainty. Measurement uncertainty is an estimate, the range of measured values, which the true value can lie. So, or alternatively, it's the amount of doubt you may have about a measured value. So in every application, there's going to be an uncertainty requirement where you're trying, or your customers are trying to meet a certain level of precision there. So the equipment used to make the measurement should be traceable all the way back up to that pyramid that was referenced earlier of standard SI Newton unit of force. So this is what's going to set that baseline, having that traceability. Next. So next reason is quality and specifications. So as I mentioned, you're going to be looking for ensuring that the component, or the transducer in this case, right, force transducer, torque transducer, is going to perform to the specifications. This is going to then ensure that you can ensure that your testing in-house is going to be tested to the quality for manufacture and also performance that you're looking for internally. So having good quality measurements, of course, is going to minimize cost per quality with using that measurement for your component or for your test. Next. Next one's minimize downtime. You want to be able to do perhaps proactive maintenance on a machine, on an article. Therefore, having good cal around that will allow you to be able to take care of things before they start to fail, right? So if you're doing periodic checks, whether it's material test frame, to ensure that it stays within spec or that it stays performing as you expect, you can then do your planned calibration intervals and minimize the downtime. Next. Data accuracy, of course. You want to make sure that the sensors you're using are still meeting the specifications. As Elliot mentioned earlier, you want to be able to do pre and post test verification so that when you finish a test, you know that the test data that you've captured is valid. You need to have that confidence in the critical measurements, and that's becoming even more true in different areas as things expand. Next. You may have accreditation or certification requirements, whether that's for the actual test data, it needs to have traceability on that test data, or you want to make sure that you maintain various accreditation in-house in your area. So therefore, of course, all components need to be calibrated and need to maintain that they have good traceable and current calibration data as part of that. Next. All right, measurement uncertainty. Next slide, please. All right, so measurement uncertainty, this is an area that we could spend perhaps hours getting into, and we probably need a little more engineering support to get to super granular level. But overall, Understanding measurement uncertainty, I think it's important to realize you have component level, you have system level, and then there's process or maybe even environmental aspects in addition to that. The goal there is to use a GUM method, which is a guide for expressing uncertainty in measurement. And that basically is established rules and uncertainty calculations around all aspects of the system or the particular set of measurements that you're taking. So next. So starts with obviously understanding what's the parameter to be measured, what are the units of measure. Then you need to go through the different components of the calibration process. And this is more so for a cal GUM, if you will, or cal uncertainty. And then what are the accompanying sources of error for those components? From that, you need to create an expression for the uncertainty for each source, and then assign a probability distribution for each source as well. Some of these equations or decisions in terms of what distribution methods to use, some of that's a function of what is the component, but some of it also may be lab specific in terms of processes and control of those processes. Next slide. Goal there is to calculate essentially an uncertainty for each source of error, right? So you're going to construct then an overall uncertainty budget that lists all the components and their contributions, each component's contributions to a total uncertainty. And then at the end, you may need to combine it all and then apply an additional coverage factor to be able to perhaps cover a full range of desired measurements. Next slide. The error that you're trying to establish for each component, of course, is going to be a function of different things. Error, as we all know, it's a difference of measured value and the true value, but that error could be contributed to mechanical aspects, it could be performance aspects, it could be environmental aspects. And so it's good to understand each of those different contribution factors and how they may impact the total budget. Next slide. Total system error, of course, it's going to be a function of each individual component. This is an example of just a load cell uncertainty data sheet where we have specifications there with regards to different aspects. Part of that too is understanding how each component is being used. I'll dig into that a little bit later, or how the test is actually going to impact which lines, for example, actually make a difference. Again, I'll get into a little more detail on that, but have to look at all the different aspects that go into it. And I think we've got a sample here. Next slide, Jamie. This is an example of a calculated uncertainty budget for an 11K reference load cell. And we've got uncertainties that even include the NIST standard calibration that was done originally. So the NIST-based cal where it was the standard was calibrated. What is the error uncertainty contribution from that? Then you have, of course, the individual reading contribution, and then you start factoring in what type of distribution factors do you want to have for each one. So there's standard deviations, triangular, rectangular. It's a function of how that's going to impact. And then there's factors from there, sensitivity, with the goal of arriving at a total uncertainty of reading on the right column there. So you've got the NIST cal, you've got potential drift and creep in the standard. Then you've got the temperature effect, which that's going to be a function of the lab, of course, too, in terms of the actual contribution there. Reproducibility aspects, noise level aspects, and then you see down here the HRBSC, that's the instrumentation side. So you've got the load cell or a torque sensor, perhaps, calibration reference standard, contributions from that. Then you'd have the contributions from the instrumentation to arrive at a total system level. So this is an example here that we've assisted some customers to come up with some direction. I would just say that a lot of it comes down to an individual lab's confidence factor in their processes and how well they can control each of these different elements. All right, next slide. So load cell errors. This is a little more straightforward here. We talked kind of overall uncertainty. Now we'll start talking a little bit about what kind of errors do you get from a calibration. So here's a sample CalCert for a 5500 series reference torque sensor. So you've got the traceability information at the top. First, you've got, of course, DUT information. You've got traceability information. There's the lab test conditions. Should be relatively static, of course, in most calibration labs. Provided shunt cal. And then we've got the performance. We've got both directions. We've got the nonlinearity hysteresis, and then we provide SEB values. And I'll talk a little bit more about what that means. But you have basically rated output in both directions for a torque sensor, and on the left there is the sample output curve. Ideally, a transducer is perfectly linear. Of course, we know they can't be. In this case, this stayed within 0.01%, so not too bad. And there's the actual cal data, both directions, or I should say at least, excuse me, it's ascending, it looks like. And so you've got some slight deviation there. This is a multiple run. E20, what is that? What is this standard again, Elliot?
E2428.
There we go. Thank you. E2428. So this is a equivalent to an ASTM E74 for a load cell. So this would be a snippet from a more extended test report that you would get than just the standard points. But the key there is, of course, that you do get a slight non-linear output from a sensor. Next slide. And again, same thing for a load cell. This is a 1610 reference gold standard. And again, you can see the slight curve that you get for an output. Next slide. So digging into some of the specifications you saw earlier for the load cell specifications, and this is a bit of an exaggerated plot here to help define. There's two primary factors that result from a calibration with regards to load cell performance, and that's going to be nonlinearity hysteresis. These are the more common aspects of a cal. We talk about in this diagram here an ideal perfectly linear output. Typically, though, when you calibrate a sensor, as we saw, there'll be a slight curve in that output as you ascend to the rated full-scale range. And so in this case, that blue portion there is the slightly nonlinear ascending load points. And then the exaggerated hysteresis on the top side is when you then take the descending points to capture hysteresis value. You end up with a percent deviation off the best, or excuse me, off an ideal straight line. So those percent deviations are what define the nonlinearity portion for the ascending, and then the descending side hysteresis, also percent deviation from linear output. Next slide. So we also provide SEB outputs for our load cells. This is essentially an error band that encompasses the ascending and descending nonlinearity hysteresis, as well as capturing non-return to zero, and provides a single point output, best fit, if you will, that encompasses all the error best possible for each particular sensor. So it's a way to take overall performance of a sensor and adjust the rated output for the actual performance of the unit. So that then establishes, instead of just the rated output, you'll have an SEB output, which would end up being the end of that output line, and is typically used if you're doing a single point scaling in your instrumentation. Okay, next slide. All right, system calibration considerations. Elliot, back to you.
Thanks, Brian. So oftentimes, it's not just the load cell that comes back for this calibration and define these characteristic performance, or the performance characteristics of each. So kind of touch on the different system level or load cell level calibration options that we have. The simplest and most common is a simple calibration of the transducer in isolation, so only the load cell. You can capture outputs from the load cell in millivolts per volt, which would be the standard native output. It could be an amplified load cell, voltage outputs, milliamp outputs, or even digital outputs from the load cell alone. The certificate you would receive would be expressed as load cell output versus applied load. It would also include a shunt calibration, which is where we apply a shunt resistor across legs of the bridge to provide a essentially simulated output. Slide, please. Thank you. So the next option is if you have other amplifiers or signal conditioning attached to the load cell, how do we handle that calibration? So there's a couple ways we can do this. Number one, we can calibrate it as a system in the rig itself, and you would receive a certificate. Essentially, the cert would be expressed as applied load versus whatever output you're getting from the signal conditioner. So typically, this would entail loading the load cell in the rig, performing the calibration with whatever signal conditioning option is included, and recording the outputs from the signal conditioner. The other option is to perform discrete calibrations of each, with the transducer calibrated at millivolts per volt and the signal conditioner scaled separately, and perhaps traceable back to a millivolt per volt simulator or other traceable device. And the other option is to calibrate each separately and use the load cell calibration data to calibrate the signal conditioner using a load cell simulator that is also traceable to NIST. Then the last option here is to perform shunt calibration, where you take the shunt data off of the load cell and use that to scale instrumentation. Next slide, please. Calibration of transducers in combination with the digital display or some other digital interface. Much like the previous option, you can calibrate these as a system or in combination in the rig with the load cell connected to the indicator. And in that case, you'd have a certificate expressed as applied load versus indicated reading. You can also have these calibrated discretely, where the load cell is calibrated in millivolts per volt, and the digital display or indicator is calibrated separately using a simulator, or a traceable standard. You can also do traceable calibrations and certs with the display interface calibrated to a traceable input. This example would be if we, for instance, had the load cell calibration. Let's say we did an E4 calibration on a load cell millivolts per volt, and we had, in this instance, a display that we could calibrate in millivolts per volt separately, or we used a CX box to essentially define how the indicator is reading a millivolt per volt input, and then provide a cert for that. So you have two separate traceable certs. This is a really nice option if you have multiple load cells with a given display, or a given display that is traveling around that you need to make sure remains traceable, or if it gets damaged, for example, in transit, you don't have to send everything back for calibration. You could simply replace a discrete item. You can also perform shunt calibration in this situation. These are very instrument specific and also application specific in terms of how these are addressed. If there's any questions on that, please contact us. Like I said, there's a lot of different options and ways to address this. Slide, please. TEDS is also a whole different animal. IEEE standard for TEDS is 1451.4. It has some defined characteristics about it. However, a lot of times it is very subject to interpretation for how that scaling data is used by different instrumentation manufacturers. And as a result, you get kind of a varied approach from each. So often the way it looks for us is the transducer is calibrated in its native output. This could be voltage, it could be a current output, it could be millivolts per volt, and then the TEDS chip is programmed using said calibration data, and a TEDS data sheet is provided with the transducer to reflect how that chip is programmed. Typically, the instrumentation is then calibrated to a traceable input. So if we provide a load cell with TEDS, we'd want to make sure that the instrument itself has a traceable cert stating how it is interpreting a millivolt per volt input. And typically speaking, these are single point scaling data type devices. There are some different templates that address the calibration data slightly different, but most commonly at interface, it's single point scaling data. Next slide, please. All right, so we'll talk about some calibration lab setup and just general tips. As with any production type environment, you will want to make sure that you have very controlled processes that are defined and recorded. That way you have technicians that are not free for interpretation. Equipment is another very important consideration, making sure you have suitable load frames or methods of force and torque application to provide an uncertainty level that's consistent for each calibration. I'm sure everyone here has seen some different equipment used, perhaps for force application. Oftentimes it's suitable, but there are limitations. For example, if you're trying to use let's say a Harbor Freight to Arbor Press for calibration, past a certain level, there's going to be a degree of uncertainty that would call into question said calibrations. Talents want to make sure that your technicians are trained and recognize the importance of the calibration process and are very, very detail oriented. That also plays to the expertise, having an engineering team to support and define these processes and make sure that the talent is trained to a sufficient level. And protocols, again, tying back to that process control, making sure things are in place to control processes and define work routines. Accreditation, that's another important one, making sure that accreditations are up to date and current and are all traceable back to your quality system. And then having work schedules and defining volumes, knowing how much you can put through the lab on a given day, so you can define work hours and schedules and making sure that you can deliver to customer expectations. Next slide, please. Best practices, make sure that workspace requirements are defined. What is the technician going to need on a given day? What adapters do they need? What procedures do they need to access for defining a specific calibration type and method? Making sure that measurement types and models are all qualified. Supplier identification, who do you go to for products or your calibration requirements? You have a torque wrench you need to be brought back into calibration. Who do you go to for that? Is it a defined list of qualified suppliers? How do suppliers get added to said qualified list, et cetera, et cetera. Touched on this on the last slide just a little bit, selecting calibration grade equipment. Making sure that the things you're using for these calibrations are of a sufficient grade of quality to provide the lowest uncertainty possible for a given calibration. Make sure that the lab is assembled in a way such that workflow is well established. So it's things are moving from the evaluation bench to the calibration queue to the calibration final inspection step, and the shipment step is at the logical flow of work between those different workstations. And again, making sure that there's a system in place to ensure your lab technicians are properly trained and qualified for each given calibration process. Certification and testing protocols, making sure that, again, everything's done to those quality requirements and there are steps and protocols in place to test to those certificates. And again, maybe a little bit repetitious here, but again, defining those workflows. At Interface, and I know other folks on here have different software that is used for tracking assets and certificates. That really helps workflow, making sure that things are flowing through to different databases. For example, pulling calibration data into a database and generating certificates and trying to avoid any manual type of calculations being needed. And then, of course, knowing your maintenance and recalibration schedules. When are your standards due for calibration? Do you have a second standard that's on a rotation to make sure you're minimizing downtime for said standard? What kind of PM is required for your cables, your adapters, the load frames, making sure if you're using hydraulic, for example, making sure that those are on a regular PM schedule to avoid unscheduled downtime. Next slide, please. Calibration fixturing. This is a critical step. And a lot of times you can see errors pop up in calibration that may not be readily explainable, that can be traced back to different issues with fixturing. This can be anything from pre-tensioning a jam nut to something that's bent to something that's starting to fatigue. So what you see here on the right is an example of a load string. This is typical for one of our load frames, and we have a series of adapters, threaded adapters, I should add, to adapt to the myriad, I should say, of different thread options that exist out there. So for tension calibration, some critical aspects to consider on fixturing. It's going to be the hardness of the material used, making sure it is of sufficient hardness, making sure thread engagement is sufficient. If you need to have a jammed nut against the load cell, that's very critical, making sure that the adapter in the load cell itself is jammed above the calibration capacity. And then, of course, making sure that that load string is concentric. If you have some sort of a misalignment or off-axis load, that will reflect at some level as an error in that calibration. Compression only considerations, making sure that the loading base hardness and thickness is sufficient to not deflect appreciably under the calibration load. Making sure that there's a single point of contact somewhere in that load string to make sure that there's not any undue misalignment error. And again, concentricity also comes into play there as well, making sure that that applied force is as concentric as possible. Again, any off-axis or misalignment is going to manifest at some level as an error in the calibration. Next slide, please. So this is just a good example. This is from our install sheet. This is a kind of a summary of the different configurations we see of load strings. So on the left here, you see kind of a more conventional loading configuration, where this would be great for tension calibration. You've got a rod end bearing installed, and then adapting through a clevis into the load string. Directly to the right of that would be a compression only example, where we have some sort of a flat platen that's fixtured into the load string, pressing against the load cell. It's tough to see there, but on that specific load cell, this is an example of a spherical surface for a single point of contact. In between that loading platen and the compression load cell is a spherically radiused loading button. So again, single point of contact. The one on the right, not quite as applicable. It could be if you were doing a tension calibration. So yeah, I suppose it could be. So this is an example with rod end bearings that are jammed into both sides. Again, you're jamming above capacity on each of those ends, and they're being loaded in tension through those rod end bearings through a clevis into the load string. Obviously, this setup would be great for tension, less than ideal for compression, so would not recommend doing that. And then on the bottom left there, last one I'll talk about here is an example of a typical load cell, how it is fixtured into the string, and you'd have a jam nut to a male calibration adapter. Again, jam nut and calibration adapter jammed above capacity. So typically we take that to between 125 and 140% of applied load, and then jam the jam nut at that point. So we do not have that jam nut coming loose above the calibration, or below the maximum calibration load, I should say. Next, please. A couple examples here. Well, actually, this is a single example, a couple different pictures. This is one of our model SSB load cells loaded into the calibration rig. You can see we've got a couple different load cells in the load string. One of these is the control load cell that provides force feedback to the frame control, and the other one is the reference standard. I believe the reference standard on this case is the load cell on the bottom, and the control load cell is on the top. That big spherical can in the center in this particular rig is our slack adapter assembly, slightly different than our standard configuration, but that's what we use on this particular frame. And the example on the right shows the loading point of the SSB. We have a spherical adapter that's been placed on the SSB, again, looking for that single point of contact. And then we have a flat thread adapter that's actually applying the calibration load to the end of the beam. And then that metal mounting surface is designed to essentially not deflect appreciably under that load. So a stiff enough surface suitable to not deflect under those calibration loads. Marcus, good question on the problem without the spherical tip. If you have a difference in parallelism between those two surfaces, you could have a moment load imparted, and it also can help with any misalignment in the actual load, or the concentricity of the applied load, I should say, as well. Again, just looking for that single point of contact between those two surfaces.
Yeah, as that load cell deflected, of course, it would start to exist at an angle, and that would likely introduce significant error in that. All right. Well, thanks, Elliot. I'll handle the next section. Next slide, please. All right. So calibration optimization, I think it's really important. I touched on this a little bit earlier, to understand that there's ways you can optimize your component level performance in an actual test based on what you do with calibration, right? So most transducers are going to have a full range standard calibration that in theory would allow as much use range as possible, right? The reality is, if you have known test conditions, you can then dial in the calibration over an optimized range. You can actually go and hit very specific target set points. If you know you're going to be testing known values, that'll take out nonlinearity hysteresis, for example, especially if it's just a single point that you're ascending to. If it is single direction, then hysteresis doesn't factor in. Hysteresis, can you guys see or hear me okay?
I can still see and hear you.
Okay, just saw some issues. It looks like Elliot might be frozen. I'll continue if you guys can hear me. All right. Again, if the test condition is a single direction only, then you can basically do a single direction calibration. Hysteresis, for example, only comes into play if you are making a descending load condition, right? So there's things such as that. You can also do an in-rig. Looks like Elliot's trying to reconnect here. You can do an in-rig calibration that Elliot mentioned earlier. And what that's going to do is that's going to basically take potentially uncertainty out of the equation for the system level, or from the instrumentation, from the cabling. And then you're looking at what's the total uncertainty on just the calibration itself, because at that point you're delivering system level measurement output against a very specific calibration load point, right? So at that point, if you can correlate that data back to what the actual test is that you're trying to do, you'll be able to take a lot of that uncertainty out of that error budget, right? So the other thing to think about is specific fixturing. We put a lot of effort and design into our sensors so that with proper installation, of course, fixturing is least amount of error source as possible during actual test. But the reality is some sensors, such as load pins, for example, can be quite a bit more sensitive. So oftentimes, if we're trying to achieve maximum precision, lowest uncertainty, we'll actually perform calibrations in fixturing that we know are going to be used in the actual test, right? So for example, for a load pin, we might do something that is representative or that is the actual test clevises or test shackle arrangement, right, for a load pin. So things to think about. There's a lot of ways that we can custom tailor, or you can custom tailor a calibration you're performing to better fit known use conditions, okay? All right, hopefully you guys can still hear me okay. I'm getting a lot of errors here. Session ended. Not sure what that means.
Still hear and see you. I think some
Okay.
people are having some technical difficulties, so
Okay.
we'll keep recording and hopefully join.
All
Have
right.
others
Thanks,
join.
Jamie. Okay. We'll keep going then. Next slide, please. All right. So we're going to do a couple apps, basically, different ways you can try to do some calibration, what equipment to use. This is an example of using one of our verification frames. Using it for calibration might be a stretch, but it can certainly work in a pinch. We found some customers to get good results from it just in that case. But in this case, it would be a 9840, perhaps a 9320 handheld instead. You, of course, have the frame itself. You'd have some adapters and some necessary fixturing. And then you can calibrate things such as maybe some load buttons or even some small mini type load cells against a reference standard. So you'd have a 1606 in there. Again, this is a 1,000 pound rated frame. So if you're doing a couple 100-pound loading in a 1606, or if you're going all the way to 1,000 pounds, of course, you'd want to use a 1610. And then you'd use the portable load cell calibration system, GSys-03. That system includes the software. Software is really important because it can capture that data, it can do linearization in many cases, and more importantly, it gives you the CalCert. And these are customized CalCerts, company information, company logos, or if you want to only have certain data or additional data reported on the CalCert, of course, the software that goes along with that would do that as well. So next slide. I would say the most common form of calibration that's out there is calibration of material test frames. So, and part of that is governed, of course, by the ASTM and the E4 protocol in particular. So that procedure outlines how you go about testing, or excuse me, calibrating a material test frame so that then your test data that you use that frame to generate is valid, right? So we have a lot of customers that have essentially put together kits that they can go and take into material test labs and can perform these types of ASTM E4 specific cals. So we'd use a 9840, again, portable, dual channel. It could be, well, excuse me, it would be single channel in this case. They also come in dual channel, very portable, very accurate instrument, very common, very popular. You'd have necessary load string adapters. It would be a function of the threading or fixturing that is already there in the frame. And of course, you'd use another 1600 series reference standard as the way to go. And the GSys04 calibration system also includes E4 specific software. So you'll have a E4 compatible calibration certificate report that comes from that. Thank you, Renee. And also generate ISO 7500-1. That's good for some of our international customers out there as well. So, so it's not only having the equipment, but it's also having the software to then be able to generate the test results, documents, not only for maybe an end user, for your customer, or for your internal record keeping, right? And the other nice thing too is, of course, our gold standard software allows for historical review to see if anything's changing over time from previous cals, for example. So next slide. Past material test frame calibration, then obviously we've got transducer cals, and the interface has a full suite of products to be able to support that, whether you want to just be able to take certain components like we saw in that first example, or full-blown automated cal frame calibration frames like we offer that's pictured there. So of course we'd have a dual channel 9840 to be able to take the DUT signal as well as the reference load cell signal, not pictured. Your reference would be a 1600 or 1800, and again, size that either for the particular cal range you want to do, or full scale on a 55K frame, of course, would be an 1830 there. So, and our GSys03 ASTM E74 software can perform or provide basic calibration certificates for standard cals or full-blown ASTM E74 cals if you're doing calibrations on sensors that you then want to use for other calibrations in-house or for customers. So just an example of taking the different components. And of course, as Elliot talked about, the linearization, things like that we offer with our software will really cut down on that uncertainty, and of course allow you to custom tailor specific set points as well for a particular cal or for a particular test range. All right, next. Fixtures. It's back to you, Elliot.
All right, thanks, Brian. Yeah, we'll give a kind of a quick synopsis of some of the different options we have at Interface for calibration equipment, metrology grade type equipment. Fixtures and adapters, this is a real common one for us. And again, we touched on the criticality of fixtures here earlier. We offer a very wide range of female to male thread adapters. They're machine to our standards and hardness specifications, including jam nuts, spherical loading surfaces, and stud ends. You'll notice on this calibration adapter here, we've got a threaded collar for jamming, or actually, I'm sorry, a threaded jam nut, and there's a collar feature that can be used with a spanner wrench to locate and then jam down. So that's a precision machined jam nut, and you'll also notice there's a spherical radius on the end of that calibration adapter, and that's if you wanted to use this for compression only type configuration. It also, as mentioned again, fixturing is a wear item and potentially a very common error source, so important to keep an eye on those items. Slide, please. Reference standard load cells, we've got a very wide range across a very wide force range as well. Kind of start at the low end here and then work up. This is our model 1606. This is a precision version of our model 1500 essentially, so it's going to have additional gauges to provide better moment or off-axis loading rejection. It includes an ASTM E74 calibration, tighter temperature and moment specifications than our standard 1500 would have, and we also guarantee a 4% lower limit factor per ASTM E74 on these load cells. So if it's more than 4%, it does not ship. Other kind of details, you notice it's got a slightly larger connector on it than our normal load cells would have. That's an 8-pin connector, and that has separate sense leads that go directly to the bridge for further error reduction. Slide, please. 1600 series is our most popular and most common metrology grade sensor. Again, it's going to have tighter specifications than our standard 1200, 1100 load cells would typically have. It's got that same sense lead connection directly to the bridge that the 1606 did. These are only sold with bases installed and with calibration adapters installed. So you'll notice that there's a calibration adapter included that is threaded in and included, or actually the load cell is calibrated through its E74 calibration with that adapter installed. It's not removed prior to shipment. Again, there'd also be a spherical radius on the end of that calibration adapter if one wanted to use that as a compression only loading configuration as well. And again, ASTM E74 calibration included, and as with the 1606, 4% lower limit factor guaranteed. Slide, please.
Hang on real quick. I want to do a deeper dive on cal adapters and why we offer them on our standards. So we talked earlier about overall error budgets, and there's certain reproducibility aspects, variability that you may have in cals. And we've also talked about fixturing and how important fixturing is, right? So the reason that we install cal adapters in our 1600, 1800 series and ship them with those in place, and it'll jump to the 1800 here probably next and talk about how we take it one step further, is by shipping the units with pre-installed cal adapters, we are essentially moving the load introduction point a little further away from where the gauges are. And we've ensured now that there's no variability in terms of how the load introduction is presented to the load cell in terms of where the beams are and where the gauges are right below that top cover. So by us covering the fixturing element, we are delivering a product now that when you put it into your test case or into your frame, is going to have even better uncertainty and improved repeatability. So that's the really important spec you want to be looking for and be thinking about when you're characterizing your own standards is what is repeatability or reproducibility. Repeatability, if you have nonlinearity in a standard, but you know exactly what it is and it repeats to that every single time, then the overall error there for that load point is going to be known and very small, right? So cal adapters, why are they important? Why do they exist in standards? Because again, we're taking some of that uncertainty and we're reducing that error budget, if you want to look at it as a total system, by us ensuring that you're going to get much more consistent load cell performance by having the thread engagement a little further away and having the threads internal to the hub all locked in and loaded at a higher than capacity range. So sorry for jumping in there. I just want to make sure we spend a minute or two on that.
All right, and you're right, Brian, the 1800, sorry, I was wrong. 1600 is next, 1601. So this is a little different. You'll notice that there is no calibration adapter at all on this one. It's simply a spherical radius, obviously not intended for tension use. This does offer the advantage of a lower stack height than the 1600 if you're performing essentially compression-only calibrations. A common example of this would be folks that are calibrating concrete crushing machines or concrete testing machines where they don't have any tension application. It's simply E4 verification in one direction. So again, you could do that calibration of the standard 1600, but this does get you a lower stack height, and it does have an integral spherically radiused loading surface and installed base on it. It gets the same 3-run ASTM E74 calibration, and is also guaranteed to have a 4% or better lower limit factor. Next slide, please. As Brian mentioned, there is a grade above the 1600, or we take it even farther. It's the positive benefits of the installed calibration adapter are built upon with this load cell. It's a monolithic design, so the thread adapter in this case is actually integral to the load cell. So there's no threaded joint inside that load cell, which further improves repeatability, as Brian referenced earlier. This load cell also has twice the number of gauges than one would find in our standard 1600 series. This has the added benefit of further reducing sensitivity to off-axis or moment loading by better balancing the bridge across the load cell. And these also would come standard with an ASTM E74 calibration, and provided that the calibration is sufficient, it is capable of a 2% lower limit factor per ASTM E74. And again, this is our highest grade of metrology calibration grade force transducer.
Yeah,
Next
I think
slide,
I saw a
please.
question pop up earlier.
Oh,
Elliot asking about what kind of improvement from integral cal adapters. And just for reference, don't hold me to a number right now. Probably would need to get some input from engineering. But for reference, our standard 1200 series has a non-repeatability spec of 0.01% of reading. Okay, you jump to a 1600 series, which has a pre-installed cal adapter. Yes, there's some other things as well, such as tighter moment specs and things that contribute, but the non-repeatability jumps to half of that, to 0.005%. So I would say most of that repeatability improvement is going to be a function of the pre-installed cal adapter. So hopefully that helped answer that question.
Thank you, Brian. So we also offer calibration grade column load cells. Those 1600 and 1800 load cells are fantastic, fantastic metrology grade sensors. Past a certain capacity point, it can become sometimes somewhat unfeasible if it needs to be portable, for example, or if it needs to be repeatedly loaded in and out of a calibration frame. So another good option here would be going to a column style load cell for these types of calibrations. For our calibration grade column cells, we do a couple of things different from our standard columns. We again, much as we did with the 1800 series, we actually quadruple the number of gauges on the load cell. Again, trying to reduce moments and eccentric loading sensitivity to provide better performance, better repeatability. These are much more lightweight than the 1800 and 1600 load cells, a lot more compact, especially radially, and also are included with an ASTM E74 calibration. We've done a lot of different variants of this load cell as well, so it's not just female to female orientation. We've done custom items. A real common one we did was for, again, I referenced concrete testing earlier, or concrete machine testing earlier. We've done some custom variants of this with just a spherically radiused upper surface that provides a very high capacity, very portable calibration grade load cell for that type of testing. So if you're on the road testing that type of machine, that can be a great option for you.
Yeah, and in controlled environments too, these perform controlled geometry, I should say, they perform very well. In fact, our million-pound frame uses a similar standard and not an LP actually on it.
This is a newer product feature here on the torque side, 5500 series. We've taken our 5400 series and done much like we did with the column. You'll see a common theme here. Double the number of gauges, again, trying to reduce sensitivity to off-axis and eccentric loading. Essentially, we've also, on some capacities, doubled the number of mounting holes to make sure there's sufficient clamp force to eliminate the possibility of any slippage in the calibration. These are available with the torque variant of E74, which is E2428, similar to E74, and then it's going to be multiple run calibration and include curve fit data. These are very, very good performing torque transducers and available in a very wide range of capacities. So let us know if you want more details on that. Yeah, 2,000 poundage to 300,000, so a lot there. 9840. It's been real
quick on those on the flange sensor. Just again, back up one slide real quick, Jamie. Elliot touched on the fact we may increase bullet holes, and that is to ensure that there's adequate clamping force. It's real important for people or users to understand that torque is transferred through that clamping pressure and not through shear loads through the actual bolts, right? So want to make sure everyone's aware of that. And of course, we'll have a tolerance fit on one end as a piloting function to make sure you can locate what you're hooking up to it. But again, that clamping force is in the friction between two flat surfaces is essentially what should be relying on for transferring the torque through the sensor. So I just wanted to touch on that. Thanks, Todd.
All right, instrumentation side. So 9840, this is a very popular device used in many hundreds of calibration labs worldwide, really, at this point. A lot of really good features. Many people may not know this, but we are not limited just to a single or a dual channel configuration anymore. We've done up to 7 at this point in time. This has a lot of great features on it. Remote sense excitation. Again, reducing any potential error due to a voltage drop across the cable run. This does do point-to-point linearization in either 5-point or 6-point. 900, essentially it's a million display counts, so lots of resolution there. It has a direct analog output and a scalable analog output as well. A little bit slower on the scalable side, but very nice if you want to scale across a separate range of the device. And for those, I would say, power users that want to write their own code or integrate into a different device, it does have duplex RS-232 communication. We've done some different options on this recently as well. I'll just touch on that offer the ability to interpret different TEDS templates, and as well as offer TEDS read-write functionality, and even adjust specific points within a TEDS program depending on how that a TEDS chip is programmed within the device. And then the next slide should touch on, this is a more modernized version of the 9840. The standard version of this is the 9840-400. You'll see that it's of a slightly larger chassis size, but it does go to a more modern touchscreen display. The standard variant has 4 inputs, so it'll take 4 channels of data in. It has the same performance, same level of performance, I should say, as the standard 9840. Again, more modernized and more graphical interface. We've done some, again, just touching on the flexibility of this. This is available in different inputs that people may not be aware. We have done versions with voltage inputs. We've done quadrature encoders. Lots of different options with the device. In addition to that, it's not pictured here, but we have a new version of this out as well that is designed specifically for torque wrench calibration type applications and has a very specific feature set for that. So we've updated the sampling rate to 1 kilohertz, and we have a special peak hold capture that is designed to capture the first peak in a torque application. So if you think if you have a click type torque wrench, and as you approach that set point for the torque, it captures that moment it clicks, as opposed to capturing that second torque peak after the click. So where you apply the torque, wrench clicks, but your arm keeps moving, and that second peak is typically higher, but that's not what we want to capture. We want to capture that first click point. So designed specifically around that. I think next slide, please. And I think this is the last one here. CX boxes. Well, maybe one more of this. CX boxes, these are incredibly useful tools. They can be used for instrumentation scaling. These use a very high-grade resistor set in a star bridge configuration, and they are designed to simulate the input from a load cell in multiple steps. So we've got 2 of them pictured here. We've got a 2-step, which is a 0 and 4 millivolts per volt in both direction. And then we've got a 6-step, which is essentially decrements of 1 millivolts per volt up to 6 millivolts in either direction. Again, these can be used for scaling different instrumentation, and if traceable to NIST, so you have essentially a traceable measurement standard that you can use to scale instrumentation. These are also incredibly useful for troubleshooting if you're having an issue with a load cell system, and you're trying to diagnose, is it the load cell, is it the cable, is it the display, is it the amplifier? These can be used, and frankly, they're a lifesaver a lot of times when you're trying to troubleshoot. So,
yeah, very, very handy and very accurate. I don't think we highlighted there, but they're stable to a few parts per million of drift annually. And the calibration data you get, I think, goes out 6 or 7 decimal points in terms of precision on the millivolt specific output. So very, very handy, very versatile, but also incredibly accurate. It's basically how we scale nearly all of our signal conditioners that we ship, unless customers do request in-rig calibrations.
So E4 calibration systems, typically speaking, this will consist of a 9840, an internet cable, and the CX box, and the software set. Obviously, normally we'd have a load cell also associated with this set at some point in time. That's going to be dependent on the force range and what form factor requirements each application has. CX box is used as a check device for the 9840. The 9840 is not actually used for display purposes in this particular setup. It is used as the A to D, and the software is communicating through the PC to the 9840, pulling data off of it, and actually stores all the standard polynomial curve fit data and standard data on the software side, and data is entered through that. Again, this is used for ASTM-E4 machine calibration, with the load cell being sized around form factor and force range requirements. I should also touch on one of the features. So we consistently get feedback on that E4 calibration is the benefit primarily. One of the biggest benefits we hear about is the automatic report generation, I should say, and customization. So it allows you to essentially have a one-click function where it's calculating performance of a calibration run. There's no hand calculation, and then customization of your calibration reports to fit your specific lab requirement. So get good feedback on that a lot. And then next slide, thank you. GSSY03, this is our E74 portable calibration system. This is typically used if you have an existing frame or force generation / application system that you want to update to use this software set, and provides the same software we use on our factory floor. Much like the E4 system, the 9840 functions as the A to D. The software is where you upload your standard calibration data and generate set point files. And then again, just to touch on it, as with the E4 calibration software, automatically generates reports, graphs, and performance that are customizable to your specific requirements. And again, primarily time savings we see there is in that report generation side. IFVF, application example earlier of this, I wouldn't say this is necessarily used for metrology grade applications, dependent on the transducer, of course, but for more on the force verification side, whether you're trying to do a quick verify or floor level check on a load cell system, or for some load cells, like Brian mentioned, some load buttons, simple load button or simple load cell type devices could do some level of calibration, particularly if you're not trying to drive to a specific load point. So if you don't need to take specific 20% intervals, perhaps this would be a good option where you're just trying to compare an output from the standard against the output from the load cell. This can be, and we have successfully combined this with our portable load cell calibration system, and it's given us great results in there. This consists of the actual frame. We have essentially a threaded rod that provides the force application through the lever on the top, or the wheel on the top in the lower capacity cases. And then you'd pair that with a reference standard load cell, perhaps a different calibration adapter set to fixture into the cell itself, or the frame itself, and then some sort of a display to indicate the values from the standard and the device under test. Also can provide these with quick change adapters, so you have a variety of different load string lengths that you can accommodate. If you either the dowel pin adjustments on the side there, or the actual adjustment of the thread itself. Next slide, please. As Brian mentioned earlier, I won't to touch too much on this, but this is kind of the top of the line in terms of what we offer for metrology systems on the system level. And this would be a complete calibration load frame. These are available in standard capacities of 55,000 pounds and 100,000 pounds. And we have two different standard heights available. So if you don't need a super long load string, there is a shorter height version available and a taller version available with various working heights. These are very nice in that the hydraulic power unit is integrated into the frame itself. So you can see we have the piston on the left-hand side of the frame. The HPU lives on the right-hand side of the frame. And this functions directly with our E74 calibration software and is even more integrated in that it has its own control feedback. So not only can you enter in your calibration data from your reference standard load cell, this will actually control and automate the calibration process. Typically speaking, you're going to see, let me back up one step, I'm sorry. This also allows you to run tension and compression in one setup, so there is no removal of the DUT and installation in a different manner or configuration to switch between compression and tension calibrations. It's a single setup for tension and compression, and you're typically speaking, you're going to see a full 5 or 10 point calibration accomplished in between 2 to 3 minutes. Very quick. Typically speaking, you're going to spend more time installing the DUT into the system than the calibration run itself will actually take. So,
yeah, a couple comments on that. I mean, these are great for reducing a lot of process control variation in your systems, right? So being fully automated, you're going to ensure that set points are hit the same way consistently. It's all controlled via the software in terms of dwell time, sample rate, how you want to actually take those data points from your DUT. But in addition, these are what we use. We have an array of frames in our calibration set up over the years, but all the newer ones are basically match this, which was what we made commercially available. So it's the same thing that we use to calibrate upwards of 85,000 plus sensors a year. So thanks.
All right, Chris, I think this is you.
Yeah, hopefully you guys can hear me. We have some technical difficulties earlier. But yeah, I wanted to talk about the calibration services that we offer for our recal business. So if you can go on to the next slide. So we offer a variety of calibration services, and these apply to not just only interface cells, but also to a wide variety of industry standard cells, both force and torque, as well as some crane scales up to about 100,000 pounds. We can do the crane scales as well. So for our force calibrations, they're NMI traceable anywhere from 50 grams all the way up to our 1 million pound capacity. We have across force and torque 11 different hydraulic rigs, 6 deadweight calibration stands to support calibration. For the torque, we can do all the way down to 0.022 up to 100,000 in pound force categories. We do also work with some outside partners for the higher capacities, which I believe we can do up to 200,000 on those as well. The calibrations are NIST traceable up to 2.2 thousand and NMI traceable up to 100,000. Next slide, please. So this is a variety of the calibration services that we offer. So we can do standard ISO 17224 A2LA accredited calibrations, ASTM E74 and ISO 376 on force. And from the torque side, we can do a standard, the A2LA Z540, as well as the ASTM E2428. And those do come with the calibration certificates that provide the additional information depending on the calibration that's provided. Next slide. In addition to doing recalibration, we also do repair services. So we have a comprehensive team repair services for interface load and torque sense transducers. Basic repair services for industry standard load and torque transducers. And as you can see below in some of the pictures, you can see some of the damaged connectors that we've replaced in the past, diaphragms. We can replace bases, repaint, and we can do this for most load cells across all manufacturers. Next slide. So why choose Interface for your calibration service? We're ISO 17025 accredited. We've got 50 plus years of calibration experience and perform over 100,000 calibrations annually. We permanently archive our test data. This is incredibly useful when it comes to recalibration because we can go back and we can look at prior year's data if something's not matching on the calibration that we have. It also allows us to provide historical data to anything that may shift or to try to get us explanations on that as well so that we can provide that information to you guys. We have highly trained professional technicians. We have a quick and timely response both on the front end from just getting an RMA set up with our customer service team, as well as on the back end, making sure the calibrations are actually performed. And then we do have calibrations running in this facility 24/6. So we have people starting Sunday night and they're here through Saturday morning. So we've got our rigs are being used around the clock. Next slide.
All right, thank you, Chris. So we'll try to touch on a couple of do's and don'ts and then touch on some frequently asked questions. This is kind of a compilation of some points we made earlier in the presentation. So do try to match the calibration of the real world application. That's important. Trying to as closely replicate the use case in the calibration frame will yield the best and most real world results for the best or lowest uncertainty in the actual measurement in the field. That can consist of replicating fixturing up to and even actually using the customer's fixtures in the calibration rig, as Brian referenced. We've got experience doing that. Load pins kind of immediately spring to mind specifically, but that can have great impact. Do consider fixturing impact on calibration. That also ties back to the first point there, making sure that the fixturing is appropriate for the calibration type being used. Flat surface to flat surface in a compression type calibration would be one example of what not to do. If you're seeing something untoward in the calibration data, maybe it's worth going back and reviewing that calibration fixture to make sure that there's not a fatigue issue or some sort of a bend. Is it bent? Is there another issue with the fixturing that's impacting that calibration? Another one that comes up pretty frequently, do you understand performance limitations of the device under test? So is the calibration selected appropriate for the DUT being calibrated? For example, if you have a small load button type device that is a 0.5% accuracy, is it worth going to the trouble of performing an E74 calibration on said load button when the repeatability may not be sufficient to justify that type of calibration? Don't underestimate the importance of process diligence, making sure that there is consistency across the workforce in how these calibrations are performed. Don't ignore calibration schedules on equipment on an annual basis. If you have multiple force standards, making sure that there is a rotation in place so you're not finding yourself in a production down type environment. If your calibration standard goes out for some reason and it's off interval with your rotation load cell. So making sure that steps are in place there. Do incorporate recurring checks for instrumentation and system level calibration performance. This means checking electronics, checking rig performance to make sure that there's nothing out of the ordinary, checking instrumentation to make sure that there's nothing, it's reading its input correctly and is not identifying errors. The last thing you want to do is to get through a day of calibration only to discover that there's an issue with the acquisition board and it's been reading off by 5% all day long. Or worse yet, you've already shipped load cells and said board was off. So calibration escape. Incorporating regular PM and testing for cables and adapters. Sometimes it's the simple things that need to be followed up on, right? Is there an issue with a cable? Is there an issue with an adapter? Are the sense leads not correctly corrected through the adapter? Have the adapter pins been fatigued to a point where they're not engaging properly and you're getting intermittent contact? The simple things always need to be considered in these types of critical applications such as calibration. And then cycle count on fixturing, as mentioned a couple times now, they do have a fatigue life, they do wear out, and it does have significant impact on calibration. Brian, anything else to add there?
No, I think that's pretty good. The recurring checks are important. Interface employs various daily, weekly checks on all of our cal frames to ensure that we're maintaining consistent performance, and of course, recognizing if there's an issue. But the daily checks, coming up with a process there, is very, very good recommendation for busy cal labs.
All right, so we get a lot of questions from customers. So these are kind of the top 10 we put together. I'm sure there's some others that we've not captured in this, but we'll kind of touch on these. A very common question is, how often should I recalibrate my transducer? And that's not for us to say. We can make a recommendation, and it's typically speaking, we recommend 1 year. That is contingent upon the usage type and criticality of the measurement. If it's a very, let's say it's a hazardous environment for the load cell and it's being used perhaps past its design considerations, perhaps that's a load cell that should be put on a shorter interval so you can find out, you can track its performance essentially, and if something's going wrong with it, you capture it sooner. Or if it's a critical measurement, tighter intervals will will promote confidence in the measurements you're getting from the transducer. If it's a calibration type environment, of course, default to ASTM E74 for justification of that calibration interval.
Yeah, but if it's a sensor you've got a lot of confidence in, you can extend that interval. We have some reference standards that are on 2 or even 3 year, I think maybe even a 4 year for some of the older ones, cal intervals, because of our extensive confidence around it. So, but yeah, first year, good rule of thumb. It's not a bad rule of thumb to follow. Zero balance checks, of course, are a good way to see if anything seems to be changing with regards to the health of the transducer.
Number 2, how do I know if my transducer passed calibration? Typically speaking, we've got an automated flag system in place with our calibration software. So if one of our load cells does not pass, it is flagged. And this is, of course, on the recalibration front. We don't ship transducers on the production side that don't meet spec. But if it does not pass recalibration per our specification, it is automatically flagged in the system and the customer is notified. At that point in time, it's customer choice whether or not they want to accept the transducer with calibration data as is. Number 3, should I send in my indicator for calibration with my transducer? That's a highly variable question. If it's a system level cal and the indicator does not have another method of providing traceable calibration at your facility, the answer is always going to be yes. More to the point, it's going to be what calibration are we going to perform at the factory on this indicator set. The example I'll use is our gold standard systems that ship with a load cell and CX box and an indicator. If you're calibrating the CX box at your lab, you can use it to calibrate your 9840, and you still have a traceable measurement, meaning you can send back the load cells, have them calibrated in millivolts per volt. No need to send it in the indicator. If you're using the load cells, if you have a dedicated load cell you're using with the 9840, and you want your cert to read as applied forces versus indicated reading, yes, it needs to come back in for calibration. If it's a gold standard system, note that you'll want to make sure that you request the indicator be calibrated separately from the load cells, as having a system calibration performed on a gold standard system doesn't accomplish anything, as we need the millivolt per volt data from a load cell calibration to enter into the software. What evaluation is done on my transducer when sent for calibration? So we perform a couple checks. Number one, it's a bench evaluation. We perform a physical inspection of the load cell, look for damage, step number one, and then document the as received condition. We then perform a series of bridge evaluations using both an indicator and then taking resistance measurements off the bridge. What we're looking for there is any potential electrical symptoms of mechanical overload or damage. Are we seeing an insulation resistance breakdown on the load cell that could be a sign of either a wiring issue or other damage inside the load cell? And of course, what is the zero balance of the transducer? We want to make sure that the sensor is in a good enough condition that, like for instance, if it has a bad IR condition and we put it on one of our calibration rigs, that causes other problems for our instrumentation. So we want to make sure it's suitable for that and make sure it is in good shape for the cal. What tolerance is held for recalibration? This is a pretty common one. And most commonly we hear this question around system level calibrations where a load cell is sent in with an indicator. We do not set tolerances, but if you have a tolerance you'd like us to hold a set to, we are glad to put that on the cert for you. Just need to know what tolerance you'd like us to hold. How and when is the zero balance of my transducer recorded? This is recorded, and this is another pretty common question. If it's a tension and compression load cell, typically speaking, we perform the compression calibration first, followed by the tension calibration, and the zero balance is recorded as the final step when the load cell comes out of the calibration frame. Obviously, if it's a compression only load cell, only one direction there, so would be recorded after that compression run. If the zero balance of your transducer has changed, why has it changed? There's a couple potential reasons why. The most common one is it's been mechanically yielded, which results in a permanent shift of said zero balance. That zero balance change is merely a symptom, I want to stress, and is most commonly caused by that mechanical damage. But there are potentially other electrical issues that could cause that zero offset, and oftentimes it requires a deeper investigation to dig into the details of why said zero balance shift. Sometimes there's mechanical symptoms we can use to verify that overload condition, and sometimes we can even provide clues specifically to how it was overloaded, but those generally speaking have to be pretty obvious for us to tell. Again, the deflections found in a typical load cell are very small, and it takes a pretty finite measurement to be able to drive to a true root cause to damage.
So I got a follow-up question to that, Elliot. Can I use a load cell if the zero balance has changed?
That's a good question. And typically speaking, our threshold is 10% of rated output. So if we see a load cell that's shifted more than 10%, our standard recommendation is to replace the load cell. There's two common factors here. Number one, if it's shifted that much, that means that the load cell flexure or the spring element is yielded, and there potentially could be a safety issue, right? How is it yielded close enough to the point where if we actually put a load on this load cell, it may come apart and damage one of our rigs? That's number one. And then number two is a performance question. Is that load cell still going to perform with that flexure yielded such as it is? So again, our standard threshold is 10%. If it's 10% or below, we can, in most cases, electrically re-zero, or simply note on the cert what that new zero balance is. What does the shunt calibration data on my certificate mean? So the shunt calibration is performed prior to the load cell coming out of the rig on a calibration run. So they'll run, let's say, a tension run, then they'll perform the shunt with the load cell unloaded, and prior to taking that zero balance. That shunt data is essentially we apply a resistor across multiple legs of the bridge, and essentially what it's doing is it's electrically simulating an applied load using a known resistor value. So this is a very high-end precision wire wound resistor, so very repeatable with very low TC. The end user can then use that same resistor value and apply that resistance across those same legs of the bridge and simulate the output that we got. We also provide a straight line conversion number that would indicate the force equivalent of that simulated output that you can use to scale instrumentation. It's getting less and less common in my personal experience for instrumentation to require that, but it can be a good reference check for load cell health. For example, being able to check load cell zero balance and then checking load cell shunt against a known cert can be a good indication of health of the load cell. So if you see deviation between your results that you're getting in the field versus the cert, that should be a flag. What is the difference between as found and final? So on the recalibration side, we provide two different types of certs. We provide an as found, actually three types. I'm sorry, I left one off here. As found, final, and as found and final. So as found would indicate that we've received in a load cell and indicator or load cell system that we performed a calibration on and indicated the values that we received in the calibration without any adjustment. So we've not adjusted the instrument, we've not adjusted the load cell. It's exactly how it came in the door. And if we had a final cert that went out with that, that would indicate that we performed some sort of adjustment to the system, meaning the indicator was far enough off that in the calibration run that we decided to do a second run and adjust the system to provide better performance results, or an amplifier was adjusted, any number of things that were adjusted in that calibration run to provide better performance results. If you receive a cert that says as found and final, that is indicative of a system that was calibrated and not adjusted or found not needing adjustment in that calibration process. All right. Well, thank you guys. We'll wrap up with a couple things here. Brian, you touching on these?
Sure. Why should you choose interface? Well, we've been doing load cell calibrations for quite a while. We've maintained accreditation, of course, across that, and delivered very low uncertainty values for hydraulic reference calibrations. So we're in the business of building precision load cells and calibrating them very accurately, and we do so in high volume. I would say we are experts in the realm. And obviously, we have a lot of customers that do choose to send their precision interface load cells back to interface for calibration. So we've got the expertise to perform custom calibrations, or perhaps to custom tailor the calibration for your particular test. We have Chris and his group on the recalibration side. We obviously have application engineers in-house also to be able to talk about your application and figure out ways to get you lower uncertainties. So I'd say we open it up to questions at this point.
Yes, thank you. I know people have asked questions during the actual event that we've actually been able to address in real time. So thank you so much. We are going to provide this recording to people that, to everyone that registered for this event, as well as it'll be on our YouTube channel, and we'll be doing some follow-up blogs and referencing a lot of the material that was covered today. So with that, I know there will be other people that will want to ask questions more directly. We will make sure you have contacts in your area. For example, we know that Jason's looking to connect, or with, we'll connect you with Marcus and his team in the Minnesota area, as well as contacts at Interface. We have a lot of internal experts that are here to help. Outside of that, doesn't look like we have many questions here, but we would definitely, like I said, are here at any time to assist you, whether that be if buying calibration equipment or you're needing help with getting your load cells, torque transducers calibrated or repaired. I want to thank everybody. Thank you, Brian. Thank you, Chris. Thank you, Elliot. Been a great conversation. Learned a lot. Appreciate your time. Oh, we got one question came in. Andrew wants to know what's the difference between the 1800 to the 3200 series.
All right. Yeah, so good question. So they are fundamentally, I would say, similar designs at heart. They're both a shear beam flexure design. 3200 series, of course, is a stainless steel version. 1800 series is our calibration grade version, right? Our platinum, best possible, low profile shear beam sensor. So the 3200 series is similar to our 1200 standard. It's going to use 8 strain gauges. It's going to be moment compensated. 3200 series being stainless steel, it's also going to be fully welded. So it's going to have welded diaphragms top and bottom. It's going to come with environmentally sealed connector. So very rugged, but yet still delivers the precision and performance of our 1200 series. 1800 series, of course, goes quite a bit further, from double the number of gauges internally to the integral cal adapter that was referenced to much tighter moment temperature specs, gets paired with a base very early in the manufacturing process and goes all the way through the process with that base. And then, of course, incorporates sense leads, and of course comes with an ASTM E74 cal. And I'm sure I'm missing a few things there, but 1800 series is definitely we throw everything at it, and engineers don't let us change them. They say that's the best. Why would you want any deviation from that, right? So I think I saw another question pop up. Do we calibrate other non-interface load cells? Absolutely. We probably calibrate, at least 20%, 25% of the stuff rolling through is non-interface. So we've got a wide range of frames, some that can even accommodate tension links, load shackles, things that, products or dimensions of stuff that we don't normally sell. But we've been able to accommodate that over, supporting calibration services over the last many, many decades. So good question. Anything else? All right. Well, I want to say thank you as well. Enjoy the opportunity here. A lot of material, very difficult to go too deep across all of metrology, but I think we touched on a few things. And of course, if anyone that's attending has more questions, we'll be happy to answer later on. So you've got one more here. Calibrating the load cell. So I think I saw the question, it popped up briefly about sending in the amplifier with it or the instrument. Yes, we'd absolutely recommend that. Otherwise, you would need the means to be able to scale that amplifier at your facility. So we would recommend, of course, anything used with the load cell, send it in. We can give you system level or component level calibrations on everything. And now you've got full NIST traceability when you get your system back, rather than then having to deal with the separate components individually.
And just as a shout out, we are doing live events. We will be in Stuttgart next week, talking with everyone at, if you're attending Autotest Expo, happy to be in there. We'll also be doing a live event in San Jose if you're going to the Sensors Expo in San Jose, June 27th, 28th, 29th. Connect with us. We have an exclusive event that we're hosting there where we'll be talking a lot about the best of force leaders and touching on calibration a little bit, but you'll have our experts in person at both of these events. So be sure to stay connected with us if you happen to be heading to either of those areas. If not, we've got experts all over the world that are here to help. Thanks everyone for your time. And we really appreciate you sticking with us in a very information-packed session.
All right, thank you. And on behalf of Elliot, he says thank you as well. Looks like you froze up again. So thank you, everybody.
Thanks, everyone.